Hey everyone, welcome back to The Explainer. Today we are literally scaling things down to the very building blocks of life. We're about to decode exactly how cutting-edge technology helps us explore the microscopic universe and how it's completely transforming the way we understand health, disease, and frankly, the materials that make up our entire modern world. Let's get right into it. So, I want you to think about this question for a second. How exactly do we measure the invisible? How do we map the molecules, the proteins, and the atoms that make up our bodies and everything around us when we can't even see them? I mean, pulling that off requires tools of just unimaginable precision.
Well, let's dive into it. What you're looking at here might just seem like your standard, maybe kind of dry SEC Form 10K filing. But actually, it is a thrilling roadmap. It's the playbook for Bruker Corporation, a company that essentially acts as the architects of the world's ultimate magnifying glasses. They are the ones building the high-performance scientific instruments that let us peer deep into the microscopic and molecular levels. To really wrap our heads around how they do this, we're going to take a quick technology tour. We'll start with biospin and magnetic resonance magic, move over to CALID for molecules and microbes, hit nano for X-rays and spatial biology, and then BEST for extreme physics. Finally, we'll wrap up by looking at how they fuel this massive innovation engine and what the future holds.
All right, stop number 1 on the tour, biospin, where we get into magnetic resonance magic.
So biospin is basically where scientists use incredibly powerful magnets to look inside bodies and even molecules without making a single cut. What's really cool is how this translates some incredibly heavy scientific jargon into real-world superpowers. On one hand, you've got nuclear magnetic resonance, or NMR, which is used to actually check the purity of our food and beverages. And on the other, you have MRI being used in high-level pharmaceutical research to study major health challenges like oncology, neurology, and diabetes.
And this breakdown brilliantly illustrates the actual physics of how an MRI works. By manipulating hydrogen atoms, we essentially get a window right into the human body. First off, an external magnetic field forces hydrogen atoms to align. Then, a highly specific radio frequency is applied, which makes those atoms jump between energy states. And it's that exact jump that generates the incredibly high-resolution images doctors use to save lives every single day.
But it's not just about hospitals. Just look at these staggering array of fields this single technology segment impacts. We aren't just talking about healthcare, though fighting cancer, infectious diseases, and studying stroke models is absolutely crucial. This very same division is actively helping develop better, cleaner batteries for the clean tech industry, and ensuring the drinks sitting on our dinner tables are safe to consume. Moving right along to stop number 2, CALID, focusing on molecules and microbes. Now, if biospin is about seeing inside of things, CAL is where we essentially weigh molecules to sniff out hazards. Crucially, CAL provides the molecular weighing scales and diagnostic test kits that keep us safe from microscopic threats. For example, ion mobility spectrometry, or IMS, is heavily employed by the military and security sectors to literally detect chemical warfare agents and explosives. Meanwhile, their PCR tools are out there diagnosing things like tuberculosis and HIV. Now, obviously in science, you've got to make sure you're using the right tool for the job. Take these two complementary techniques. We use GCMS, that's gas chromatography mass spectrometry, for volatile compounds, which is perfect for forensics and toxicology. But we need its sibling, LCMS, liquid chromatography, to tackle the heavier, non-volatile compounds you'd find in really complex life science samples and pharmaceuticals. And all of this builds into some truly incredible diagnostic tools, like the liquid array PCR process. What happens here is that these clever lights-on and lights-off probes attach right to a sample. Then, as the temperature rises in what's called a melting curve analysis, these probes detach and emit specific light signatures. The result? Doctors can detect over 500 genotypes, like specific tuberculosis mutations, from just a single tiny sample. It's a real game changer. All right, let's zoom in even further for stop number 3, nano, covering X-rays and spatial biology. Before we get completely lost in the tech here, let's quickly define a major focus of this segment, spatial biology. It sounds super complex, but think of it as basically Google Earth for our cells. Instead of just knowing what genes or proteins are present in a tissue, spatial biology allows researchers to see exactly where they are operating inside that tissue structure. And that is totally revolutionary for developing new disease biomarkers. So these nano instruments give us literal atomic-level resolution to help build the future. Take scanning transmission electron microscopes, or STEM.
They pass an atom-sized beam of electrons through a sample to map exact atomic locations. This is exactly the kind of fundamental, foundational science required to build the next generation of computer chips, advanced batteries, and even quantum information systems.
I mean, just pause and imagine the scale we are talking about here. The exact same division providing tools for single-cell, 3D visualization of the human genome is also using X-rays to authenticate ancient art and archaeology. Plus, they're testing the structural integrity of metals used in aerospace and automotive manufacturing. It is all connected by this fundamental need to understand the very building blocks of matter.
Which brings us to stop number 4, best. Diving into extreme physics and superconductors. This segment takes a pretty sharp turn into the extreme physics and the highly specialized materials that make literally all the other superpowers we just talked about possible. Because without these supercooled superconductor wires, the entire industry would just stall. The massive ultra-high field magnets required to run the clinical MRIs in your local hospital, or the bleeding-edge magnets used in fusion energy research, they simply wouldn't work without the low and high-temperature superconductors engineered right here. And this material innovation stretches way beyond just magnets. Take this engineered product called cupanol. It's a high-conductivity, copper-clad aluminum that gives aerospace engineers all the desired surface properties of copper, but completely bypasses the heavy weight of solid copper. Lighter planes mean massive fuel savings up in the skies, proving that microscopic material science has huge, real-world macroeconomic impacts.
All right, stop number 5, fueling the innovation engine.
So you might be wondering, how on earth does a company actually sustain this level of scientific output and stay ahead of the curve? Well, this direct quote from their SEC filing pretty much tells you everything you need to know about their corporate philosophy. They don't just sit back and participate in the market, they actively push the boundaries through a relentless investment in R&D that literally exceeds the industry average. Plus, they aggressively pursue strategic acquisitions to make sure they keep their technological edge across all these different disciplines. But hey, let's be real, it's not all smooth sailing and easy science. Every single day, they are fighting on this microscopic battlefield. They have to constantly outpace massive competitors, some of whom have way deeper pockets. They face the constant risk of rapidly changing tech, making their tools obsolete. And on the operational side, they have to navigate these incredibly fragile global supply chains just to secure critical, single-source raw materials, like specialized X-ray tubes or ceramics, that they absolutely need to build these advanced sensors. And that brings us to the end of today's explainer. I want to leave you with this one final thought. We have seen how magnetic resonance, mass spectroscopy, and extreme physics are currently reshaping our world. But as these ultimate magnifying glasses get stronger, faster, and even more precise, what entirely new frontiers of human health, quantum physics, and material science are just waiting in the dark to be discovered? Thanks so much for joining us, and keep questioning the invisible.